All right, so if I gave you this one, if you take a look down at the bottom, and again, I picked this because we've already worked with this. If I started with this reaction that we have down here, silver solid is added to a solution of zinc nitrate, the answer is we already did this in the very, very beginning. It's no reaction. This does not happen. So this will not make a cell that will react spontaneously. On the other hand, it doesn't mean that we can't have this drawing, but instead of having a voltage up here, in order to make this happen, we're taking something that's not spontaneous, a no reaction. You know, silver is not going to displace zinc away to make the silver ion, not spontaneously. But on the other hand, we can drive this. If we input a voltage by way of a power supply, now we've taken this and we're going to make this happen. This will actually operate. Electrons will flow in that direction if we hook it up to a power supply. So we can cause this to happen. We just have to interfere. We have to drive this to occur with some sort of outside interference. So again, it's a non-spontaneous process, but with a power supply, basically it just reverses that. So long story short, if you encounter a problem on an AP exam that has a power supply, you got to totally reverse your thinking. It's also the same thing that we use when we want to electroplate something. We can place metals into solution and we can actually plate those metals. Chrome on car bumpers years ago. We could put chrome in solution and put an iron car bumper in there, and we could actually use an electric current to plate that. Comes into some really, really good stoichiometry questions when we encounter those, some lengthy stoichiometry problems. And I'll work through one of those here with you just real quick so you kind of understand what to do. This is going to be an electroplating, not a battery charger, not a power supply making that happen. But on the other hand, maybe we encounter a question that says, how long must 5.00 amps be applied to, let's go with another silver solution, Ag+, maybe silver nitrate, to precipitate 10.5 grams of silver. And I'll do one of these. I said I would do two of them, or I said I would do one, but I'll go ahead and do a second one. I'll do one kind of in this direction and one where we kind of go back the other way, maybe staying with the same equation that we have here. So how long must that be applied? Well, it's stoichiometry, but now we're going from grams of something to ultimately some period of time. So we're going to start with 10.5 grams of silver. And the setup's going to look something like this. From grams of silver, we're going to go to moles of silver. So we're going to look up that molar mass of silver, and it's 107.9. And now we're going to go from moles of silver to moles of electrons. 1 mole of silver, 1 mole of electrons, Ag+, single electron. And you can use Faraday's constant here or not, and I'll kind of show you both real quick. I like to go without Faraday's constant. I remember these values a little bit easier, but 1 mole of electrons is 6.022 times 10 to the 23rd electrons, Avogadro's number, and then 1 electron, single electron, not a mole of electrons, carries a charge of 1.6 times 10 to the negative 19 coulombs. Now, if you put in Faraday's constant, it's coulombs per mole of electrons, so in place of Avogadro's number and the elementary charge, we can also use the 96,485 or 96,500 value there and do that in one less step. So this is going to tell me how many coulombs that I need in order to make this happen. So I'll run the numbers real quick. 10.5 times 6.022 times 10 to the 23rd times 1.6 times 10 to the negative 19th. And on the bottom, 107.9. Divide that total quantity by 107.9. And I end up with 9376 coulombs. And this says 5 amps. So now I'm going to throw a little bit of algebra in here. 5 amps is so many coulombs per, write that out, some number of seconds. So we've got 5.00 amps is 9376 coulombs per how many seconds. So we're ready to solve that, so divide that by 5. I could have done that in one more step on the train track as well. For some reason I jumped out here to do algebra, but I ended up with 1875 seconds, or 31.3 minutes. So we would have to do that for 31.3 minutes just at 5 amps just to precipitate 10.5 grams of silver. So here's kind of a problem just like that, but done a little bit in reverse fashion. 7.5 amps for a period of 10 minutes. So we hook these up to a power supply, and we put a piece of metal down inside of a copper solution, and we want to plate the copper onto that metal. Again, this is electroplating, and I want to know how many grams of precipitant theoretically will precipitate. I could actually do a percent yield calculation. If I did this in lab, I could see how many grams I actually precipitate onto that other piece of metal. I could be precipitating copper on copper, or maybe I put a nickel down in this solution and I electroplate a nickel with copper on the outside by using a copper 2 nitrate solution. So again, 7.5 amps for 10 minutes. Of course, the amps is a coulomb per second ratio, so I need to convert that 10 minutes into seconds. So that is 600 seconds, 7.5 times 600. So basically this says 4,500 coulombs are supplied into this, and how many grams of copper would we expect to precipitate? So this is kind of backwards stoichiometry from the problem a moment ago. So now we're going to go from coulombs. Again, we can use Avogadro's number. I'll use Faraday's constant in this one. I could use either one. So 96,485 coulombs is 1 mole of electrons. If I hadn't used that, I would have went coulombs to single electrons, and then electrons, Avogadro's number, from electrons to moles of electrons. This allows me to do all that in one single step there. And now, moles of electrons. Well, this is copper 2, so this one's a little bit different than the previous one. In this one, we have 2 moles of electrons, because it's copper 2, gaining 2 electrons to make copper, 2 moles of electrons, for every 1 mole of copper solid that we're going to form. And then lastly, 1 mole of copper is grams, let's see, 63.55 grams. So kind of the opposite of the problem that we did before. Now we're actually going to solve for a theoretical yield here in grams. So multiplying across the top, 4500 times 63.55, and then divide that by the quantity of 96,485 times 2, and I end up with 1.48. We're 2 sig figs here, so let's call that 1.5 grams of copper that we would theoretically precipitate. Again, you might do that lab and maybe not get 1.5, maybe you only get 1, so then you could do a percent yield. We got 1, we calculated theoretical yield of 1.5, and that's a 67% yield if we would have numbers like that from a lab.